We are here with Nar Ganapathy, and we're going deep in Windows. And Nar is an architect for the I/O manager in the kernel. How are you doing? Thanks for talking to us.
It's a pleasure to talk to you guys. I own a part of the kernel called the IO Manager. As you might know, the IO Manager is really the component that sets the IO architecture for Windows. So whenever you call when an application does any sort of file IO, reading and writing files, downloading something from the camera, or showing something on the screen, it goes through the IO subsystem, and so it's very core part of Windows, and it's also the component that exposes the driver model. So it produces the fundamental. It actually sets the framework for writing a driver in Windows. So in addition, I am also the architect for driver model in Windows. So as time has evolved, as Windows has evolved over time, our we find the necessity to evolve the driver model as well. The devices that the IO Manager was originally designed for devices in 1989 and 1990 and around that time frame, and the devices we see now are very different from the devices it was originally designed for. And so we find that there are a lot more devices, there are a lot more variety of devices, and there are a lot of drivers. So if you look at the IO system when it was originally designed and the driver model, it was not designed for having like tens of thousands of drivers. So IO nowadays drivers are actually on par with application. There are lots of drivers. People are writing drivers outside Microsoft, and so we should actually these days treat drivers in a very similar manner to applications. Whereas in the past, drivers were this esoteric, community who used to know all the details of the kernel, who had very key access to the kernel developers and could write drivers. It's not true anymore. We need to have platforms, frameworks, libraries, tools, much like Visual Studio. So my team was formed. I have a team too, and my team is working on improving the driver model so that we get better quality drivers written for Windows. So my team has providing driver frameworks and other libraries, as well as many tools. So I can talk about that
Please.
in the future.
Fantastic.
So about my background, so I'm not a long timer in Microsoft. I've been here only for 6 years. But before that, I was exclusively in Unix. So I do bring a Unix perspective to Windows. I worked on many aspects of Unix. I've ported many versions of Unix. I've also worn key parts of memory management in Unix. So in the past, I was at Silicon Graphics and worked on IRIX and supported multiple page sizes, general purpose support for multiple page sizes. So I worked on different parts of the operating system. So working in I/O is like a very interesting job.
Now that brings up an interesting point. When we talk about the Unix kernel and the Windows kernel, they're relatively similar in their core design, in that they're macro kernels,
right,
etc.
Mm-hmm.
So, in your particular branch, how much has it evolved since NT4?
So the basic I/O model hasn't evolved as much, but I should say that there are in I/O there is a very significant difference between Unix and NT, right? For example, the NT I/O model is fundamentally asynchronous, and the layering is built into the I/O system. And at least in the Unixes I used to work with, we never had a dedicated I/O subsystem. There used to be the kernel, and the file system was part of the kernel, and the devices were attached as a file system, as part of a special file system, at least in System 5 Release 4. Whereas in NT, there is a well-defined layered architecture for I/O, and the I/O subsystem is part of the kernel, and the file system is really just another driver that plugs into the I/O subsystem. So it's actually much more modular. And so, in fact, I would say that the original NT designers, when they designed I/O, the fact that they made it so flexible is what has held us until now. The fact that Windows has evolved and it's supporting so many different types of devices is because of the original layered design of I/O subsystem. But what we are doing now is actually trying to provide richer frameworks for writing drivers in the kernel. So for example, since the NTI system is fundamentally asynchronous, and we have added plug-and-play power management, the model has become really complex. So if you want to write a driver for Windows, it's much harder now because you have to write code to handle plug-and-play, arrival and removal of devices, code to handle power management, what happens when you hibernate the machine, put the machine to sleep, code to handle asynchronous I/O and so on. And it turned out that while the system provided all the basic hooks, it left the drivers to implement most of the code. So even though you were writing a simple driver and you really didn't care much about power management, or really didn't care much about plug and play, then you still had to write all the code. So this meant that every driver had to carry lots of code, and they typically were cut and pasted, and they had errors and all those things. So we are coming up with a framework which is built on top of the I/O system, where we do a lot of heavy lifting for the driver developer, right? And this is called the Windows Driver Foundation. And in fact, this has been announced at WinHack.
Okay.
And what we are trying to do is, you can now, it's just like the .NET framework. In fact, we stole a lot of ideas from .NET framework. So we have the original I/O system was actually not a completely object-oriented system. It was meant for low-level access, high performance, high throughput, and those kind of things, which were important in 1989. But in 2000, interface design and abstraction is much more important, in my opinion at least. And so we are actually providing an object-oriented model. There are very well-defined interfaces. In fact, all our interfaces have methods, events, and properties. Very similar to what. In fact, you could take our model and you could imagine writing the code in C#, right?
Uh-huh.
But when the code is still in C, because the kernel, we still need to write an unmanaged code because that is the support we have in the kernel. But the abstraction, the model is very similar.
Fantastic. So that brings us into the next point. Your team is doing work and experimenting with managed code.
A little bit,
You're
yes.
thinking about it. And that's an interesting concept, in other words, to have type safety and verifiability in the kernel.
Right.
But of course, there's the performance considerations of a GC.
Right. Well, there are two or three problems. So with managed code in the kernel, we have a person in my team who's very passionate about it, and he really wants to get it done. And even has a couple of prototypes where he shows some of his work.
Outstanding.
But there are some challenging problems. The first challenging problem is with the garbage collection, and the second one is performance. Now, garbage collection and performance also go hand in hand, but there are also some problems in the kernel where you really cannot suspend threads. You have to make forward progress at certain times. So, for example, when you're doing page file I/O, right? I mean, I'm writing to the page file to back up some memory, to free up some memory in the memory manager. You have to make forward progress. So you really cannot at that point say, "Oh, I cannot fail. I'm raising an exception." You can't do that. Similarly, when you're there are times when the system is going to get an interrupt, and if you're running managed code and interrupt and something happens, you get an exception. Currently, the operating system is not built to handle an exception in the interrupt handler. That's in fact that is a fundamental principle behind the way OSs are typically designed. Is that you never take an exception inside interrupt handler or at a higher interrupt, because when you want to, there's no. It's mostly the way the architecture is designed. Long term, you can imagine an operating system where this is possible, but the performance overhead of implementing that is like very high, right? So especially on a commercial kernel that's been out for a long time with baseline performance, right? You certainly don't want to do anything to disrupt that. So taking an exception inside interrupt service routine is actually a very fundamental change. So, but as I said, we are prototyping it. So that is one of the approaches. But we also have projects where we are going to migrate drivers from user mode, kernel mode to user mode. So think about many of the USB devices that we have. I used to have one here, like your camera, right?
Sure.
Your mouse or keyboard. Many of these USB devices, they are protocol bus based. And they don't have like very tight latencies. They don't need to access hardware registers and so on. So it's actually foolish to actually make a foolish write driver in kernel mode to support those devices. We could really simplify the model by moving the driver to user mode. So that is exactly what we are trying to do. We are trying to move as many of the devices which don't have specific constraints to user mode. All USB devices could be written in user mode, I think, and all 3094 devices could be written in user mode. Device drivers for 3094 devices could be written in user mode. So many virtual serial port drivers could be written in user mode, and so on. So in fact, in Longhorn, we are going to have drivers for media players, cameras, cell phones, all those things, and they'll all be written with user mode, our user mode driver framework.
Fantastic.
So in fact, long term, I think that only drivers for storage, file systems, and networking, and probably display should be in kernel mode. I believe that all other device classes could go to user mode.
Really?
So imagine imagine how. So there are two benefits to that. First of all, bugs in drivers don't crash the system. In fact, my primary goal is to improve driver quality. We want less blue screens.
Sure.
And if you look at the crash data, most of the crashes are caused by bugs in device drivers. And since the driver is running in kernel mode, if there is a bug in it and it corrupts some memory, there's no choice but to bug check the system, because you don't want to propagate the error further. So we cannot recover from that error. So we have to bug check the system, and that's why you see a blue screen and they have to reboot the system when a driver crashes. So by moving these drivers to user mode, we actually remove a whole bunch of code from the kernel, and that means that you have less bugs in the kernel, and so you'll have like less blue screens, right? So that's a direct benefit. And so that is in fact our primary goal, is to make to actually improve the quality of drivers in Windows, and thus improve the end user experience.
Now, so what does that mean in terms of performance? Can you do this because of the increase in processor speed and the increase in memory? So when the kernel obviously is the most performant place to be, since it's free reign, ring zero. Mm-hmm. You own memory, you own it all.
Right.
So explain. I mean, how did you get around the problem? How do you move a kernel from? Sorry. How do you move a device driver from kernel mode to user mode? What does that look like?
So that's a good point. I can probably use the blackboard.
Sure, please do.
Whiteboard. So, we actually thought about this problem for a while, and so we decided that we only wanted to move the driver to user mode. We wanted to preserve everything else. Mm-hmm. So when you talk about the I/O system, there are a lot of things that go along with it. When an application talks to does some I/O, it needs to know what device to talk to, right? It needs to know its name. There's security involved in it, right? And then there's there's a plug and play events, the device can arrive and go, notifications and such things. And we decided that we want to leverage as much as possible, right? So you really want the application to not change at all. In fact, the application shouldn't care whether it's talking to a kernel mode driver or a user mode driver, right? Sure. So the way we do it now is actually by doing some sort of a proxy. So you have supposing this is the application. So this is the user kernel boundary. Then this is the I/O manager. So if you had a kernel mode driver and this application was talking to it, then this driver would probably be sitting below the kernel mode, below the I/O manager. Okay. So if you want to write a user mode driver, what we do is we replace the kernel mode driver with what is called a reflector. And we reflect all IOs to a host process. And we actually load the driver inside the host process. So the user mode driver is right here.
Interesting.
So this essentially the application is actually talking to a proxy driver, right? And this driver is the one that takes care of all the IOs and forwarding them to the reflector and back. Clearly, there's a performance impact with this kind of an architecture, but we find that if you look at a typical USB device or a typical many of the current serial buses, you can really maximize the throughput on the device, even though you are taking this overhead.
Sure.
And again, remember NT-IO is fully asynchronous. So while you might have a latency increase, right, you can still maximize the bandwidth on the bus because you can do a bunch of IOs, you can queue them all. So you really can. So we found out that, for example, we could actually maximize the throughput to actually a media player.
Wow.
You know, we can download music, you know, as fast as you could, whether it's a kernel mode driver or a user mode driver. And so, but there are a lot of other advantages as well. In the past, the application's behavior was actually at the mercy of the driver inside the kernel. So the kernel had, the driver was God. It could actually access all this address space. You know, it could do anything it wanted in the application. And that's why, you know, if there is a bug in the driver, we bug check the system, right? Sure. But because of this approach, if this driver was behaving badly, we could in fact terminate this process, right, and restart it, right? And we could, I mean, in fact, the rest of the system would still be available. You might see a disruption in the service for that particular device, you know, but the rest of the system would still continue running.
And the application could actually handle the exception.
Right. The application could get a failure saying, "Oh, your device went away," or we could say your status device, you know, something like that, right?
Excellent.
And so the application could recover from that error and probably do something intelligent. So that is our current approach, is to see, you know, if we can actually do this. Over time, we want to actually improve the performance. Like, you know, the way to improve this is by using very smart inter-process communication mechanisms in the operating system.
Okay.
And we are also coming up with methods by which we can actually not copy buffers. You know, like, so the important thing about any IO system is to make sure that we can transfer bytes from one point to another. That's what IO is.
Sure.
Right? Just transfer bytes from A to B. So, and we want to minimize as many buffer copies as possible. And so there are tips and techniques that we are thinking of and to improve that by providing handles and all sorts of things.
Fantastic.
So, so that's our current approach. But I can show you a user mode driver. Right?
Absolutely. Let's check out a user mode driver.